All right, so just you don't need to write anything while he's writing. It's just a real quick intro to the lesson and kind of where the formula comes from for today. So here we go. Just watch.
In this segment, we're going to talk about a technique which will allow us to calculate exactly the volume of a figure that is intricate like this one. We're actually finding the volume of glass that composes this little candle holder. And it turns out that we can find the volume either with or without the candle included. Well, the technique involves the basic technique for a definite interval. And let's talk about that a little bit. Remember that when we talk about integration and definite integration particularly, we interpret that idea as the area under a curve. And we talk about the area between the graph of a function, the x-axis, and within a certain interval. And we talked about the concept of that as being one where we first take little bitty rectangles, and if we add the sum of the areas of a bunch of rectangles along here, then we approximate the area, and then we talk about the limit of a sum and so on. Well, we're going to apply that same idea to volume. Now, let's begin a discussion of volume like this. Now, I'm just taking a very simple type of figure and a predictable type of figure like a cylinder. And we know that to calculate the volume of this cylinder, the formula is pi times radius squared times height. So pi r squared h. Now, I want you to notice this, though, about the formula, that it is the area of the base times the height. Now, in order for us to apply our integration technique to this, what we're going to do is we're going to position our cylinder in a particular way along our coordinate plane. That is, we're going to take it and we're going to just twist it a little bit and position it like this. Now, notice that the x-axis is going right through the middle of it, and I might even position, just for convenience, the y-axis going through, right about here. Then I'm defining an interval from 0 to whatever point this might be. You see, to the spot where it comes out. Okay, so that's the idea. Now, the concept is that we're going to just think about the sum of a bunch of little volumes. And it's the volumes of little disks, hence the idea of disk method. But if we just kind of take a cross section like this, and the thickness is kind of arbitrary at this point for this disk. So if I just make a cut through this rascal and think about that, and if I twisted it toward you and blew it up a little bit, it would kind of look like this. It would just be a circle, and it has some thickness to it, though, so we can think of it as a little bitty cylinder, you see. And so the volume is pi r squared times the width of this. See, we're thinking about little widths now, and it's the idea that we're applying the same concept that we did before, that we're going to find the volume of many such little disks, you see, and then we're going to narrow them.
Basically what he's talking about is, so when we first did integration, before you even learned the integral symbol, we found the area of like 3 rectangles and then added them up. Like we did a Riemann sum. The whole idea of integration is you guys are finding the area of infinitely many, infinitely small rectangles and adding them up. That's what integration does. What we're going to do today, instead of finding the area of a bunch of rectangles, we are going to be finding the volume of infinitely many small cylinders and add them up. So it's the same idea. We're taking, instead of rectangles now, we're going to apply that principle to cylinders, and that way we can find volume. That's what he's talking about here. You guys ever seen, man, you guys are getting too young, but you know how you have a spool? You ever seen where there's a bunch of CDs on a spool? It's like a whole bunch of stack of CDs. You know what I'm talking about? Some of you have never seen one. I don't know what you guys see anymore. But imagine taking that spool of CDs and turning it sideways. That's what he has here. Imagine this being a whole bunch of CDs. And what integration does, it takes the volume of one of those CDs and then the volume of the next one and the next one, and it adds them all up, and then you get the volume of the entire figure. That's really what's happening here, is that one little thing that he cut out. Imagine that being one CD that you find the volume of. And now we just need to find the volume of all of them and add them all up. That's what integration does.
Limit of the sum idea will give us the overall volume. All right, so that's the basic idea. Now notice the notation here, big R squared, for the radius of this. And when we talk about a little volume, a little delta volume here for the little disk, it's pi R squared times some delta X, some X interval, you see, over which we are slicing these little pieces of our cylinder. The overall volume is the limit of a sum, you see, of this expression, and it's just been rearranged to accommodate the situation. Now notice the delta, the thickness is approaching zero here in this limit idea. This radius is associated with an X subscript I, if we're kind of counting the intervals you see along our cylinder and the delta X business. Well, all of that leads us to integration, and the volume then is the integral from A to B, the integral within an interval, you see, of the R of X squared, and that's this part, and then the delta X is the dx, the pi as a constant comes to the outside. And all we have to do then is apply the idea to a specific problem.
So I'm going to write that formula on the sheet, but basically what we're doing, like the one formula you guys have to know today is the volume of a cylinder formula. That's what we're doing. The volume of a cylinder is pi R squared H. And that's the formula that we need to use. That I kind of cuts off on the bottom there, but that formula that he has down there at the bottom of the video, and you guys, I can't point at home, but you have your pi, you have your R squared, and the height of the cylinder, that's what the dx is. The height of the cylinder, guys, is like the part that connects the two circles here. Like that's the height of the cylinder. But when you get so small, we call that dx. Like that width between one circle to the other circle is dx. That's all this is. This is pi R squared, and then your height is dx. And integration just finds the volume of infinitely many, infinitely small cylinders and adds them up. Like that's what integrals are doing. So we're going to jump to the notes, and we're going to apply this process of the disk method. This little rascal. All right, so stop share, new share, share screen, Elmo, boom. That was faster than 35 seconds, but you weren't timing me that time. Yeah, that was fast. Okay. So sometimes there's going to be some things that you have to take into consideration throughout these problems, okay? Yeah, there's only one formula you have to know. It's pi R squared H. But there's some things that can happen. Sometimes the problem is going to have you revolve a region around a horizontal line. Sometimes the problem is going to have you revolve the region around a vertical line. And depending on if you are revolving a region around a horizontal line or vertical line, determines if you're working in terms of X's or in terms of Y's. So we'll get into that, but those are some things we have to have in our mind, just kind of in the back of our mind. But here's our formula that we need to know. If we are spinning, what's going to happen is, and you guys look at this first problem, they're going to define a region in the coordinate plane, like a 2D region. They're going to give you that region. Then they're going to say, hey guys, take this region right here and revolve it around a line, and you're going to be creating a three-dimensional figure. Now, I have some students that are very good at visualizing, and they attack it that way. I am terrible at visualizing. Like, I can't see things happen in my head. So I'm going to try to give you guys some like hard and fast ways to do these problems, and it works every single time. Okay, but we're going to take this and we're going to spin it, in this case, around the x-axis. So a horizontal line. Picture this 2D region revolving. So imagine the top of this curve kind of coming off the paper and then going down to the paper and then into the paper and creating what looks like a football or a lemon, if you will. You're creating like a 3D shape. Can you guys picture that? I'm not good at picturing it, but that's what's getting created. Well, when you spin around a horizontal axis of revolution or a horizontal line, here's your formula. We're going to integrate from A to B. So whatever the most left value is to the most right value. You can put the pi inside of the integral, but I always like to take constants and pull them outside. It's going to make your integration a whole lot nicer when you're not working with that pi inside the integral. So you have the pi on the outside. You're going to have a radius. squared. Now, when I say the only formula you guys have to know is pi r squared h, that's what it is. That's what this is. This is pi radius squared, and then your height is just dx. It's that infinitely small distance between the two circular bases. The hardest part about these problems, and I'm not going to say it's a hard part, but the hardest part is figuring out what is the radius. What is that function that we need to put inside the integral? That's what we're going to spend most of our time on today, is how do we find that function? So let's dive into this first problem. Okay, so I have this region where we're spinning it around the x-axis. Okay, so I'm going to set up my volume formula. Volume equals pi, the integral. Now we're integrating from 0 to pi. Now we have to find our radius. So here's how I like to think about what the radius is. Okay, so first of all, imagine this region, like I said, spinning. I'm the worst artist possibly known to man. Like, it's possible. So here's our 3D region. That thing's coming. That's just so bad. But anyway, so imagine this thing spinning, right? You have a 3D figure. The radius is going to be half. So imagine we like slice through this thing and create a cylinder. Take a butcher's knife and you're like, ah-ya! And you pull out and you create a cross section that's like a cylinder. Okay. The radius is going to be half of this figure. Here's how I like to think about the radius though. I'm going to do this in terms of rectangles. This whole lesson, I like to think about rectangles. And here's what I do. For my radius, I'm going to draw a rectangle. And I'm always going to draw my rectangle from the axis of revolution, from the line I'm spinning around, all the way out to the function. So I'm going to draw a rectangle from the x-axis up to the function. Doesn't matter how big you make the rectangle, it's just a representative rectangle, just to give us a visual. Whatever the height of that rectangle is, that's the radius. That's half of that cylinder that's spinning around. Let me say that again. However tall or whatever the height of that rectangle is, no matter where I draw it, I could have drawn it here, I could have drawn it here, but the height of that thing is my radius. What is the height of that rectangle? What's the height? No matter where I draw it, what's the height of that rectangle going to be? The function value. Like right here, whatever the function value is at this x, that's the height. Here, whatever the function value is, that's the height. Whatever the function value is here, that's the height. So our radius is however tall that rectangle is, and that rectangle is just whatever the function is. The function is the square root of sine of x. So it's going to be the square root of sine of x squared, and then dx. Once we do that, now it's going back 2 months ago and doing this stuff, like doing the process now. So I'm going to have the integral from 0 to pi of sine of x dx. Bless you. The integral of sine is negative cosine. It's easy to screw that up because we differentiated sine so often, right? The derivative of sine is cosine, but the antiderivative of sine is negative sine. So it's pi and then negative cosine from 0 to pi. On that test I gave back, there was quite a few people that forgot to integrate. That they set up the integral and then plugged in the top number for the function and then the bottom number. Like they never integrated. I've made a lot of comments on a lot of tests like, you need to integrate first. So don't forget to integrate. Now I plug in pi and plug in 0. Remember, if it's an FRQ, you can leave that answer. You don't have to evaluate trig functions on a free response question. Just keep that in mind. We're going to, but so it'd be pi, and then cosine of pi is -1. So -1 is 1 plus 1. 2 pi is the volume of that figure. 2 pi. as we go through the examples, the hardest part of the problem is finding that function that we're going to put in there, because it's not always just going to be as easy as whatever the function is, that's what we plug in and square. I tried to make this problem like the easiest to start off with, but there's going to be some other things that we have to think about as we kind of go through the practice. Okay. Next one. So like starting with the next one. So it says find the volume of the solid formed by revolving the region bounded by 2 minus x squared. So that's our parabola. And g of x equals 1 about the line y equals 1. So in my mind, I've done a lot of these. So I'm going to tell you kind of the catalog that goes through my head. First thing I do is think, what is the region that I'm spinning? I start there. Like where am I bounded? So I'm bounded by the parabola and y equals 1. So the parabola and y equals 1, that forms this shape right here. Okay. The second thing that goes through my head is, am I spinning this around a horizontal line, or am I spinning it around a vertical line? Like we haven't done that yet, but that's the next thing that goes through my head. Because that tells me, am I in terms of all x's, or do I need to be in all y values? Like with respect to y, like when we did area between curves and we did right minus left, same idea. So those two things go through my head. The third thing that goes through my head, we haven't talked about it yet, but do I need to be dealing with a washer problem? Now I want to talk a little bit about what that means ahead of time before we talk about it. Notice on this first one, the region I was revolving was flush with the x-axis. It was completely flush with the x-axis. There was no space between the x-axis and the region I was spinning. That's a disk problem. Notice on this one, I'm spinning around y equals 1. I'm not spinning it around the x-axis. I'm spinning it around y equals 1. I could ask both of those questions. So I want you guys to see the difference here. When I spin this region around y equals 1, so this line right here, notice again, I'm going to create, it's all flush. That region is flush with y equals 1. There's no space between this line here and the thing I'm spinning. That's a disk problem. However, if I asked you guys to spin that region around the x-axis, now try to visualize that. Now try to picture this whole region coming out of the paper and revolving around the x-axis. There is space between the x-axis and that region. That would be a washer problem. We haven't talked about that yet, but those are all the things that go through my head. I find the region. I'm like, am I in terms of x's or y's? Is it a disk or a washer? Like that's the catalog that I run through in my head. Once you do that, then finding the r's is where all the fun begins. All right, so let's do this. So it's going to be pi times the integral. Well, in the last problem, it gave us our limits of integration. This one didn't. So we need to find the things that we are integrating from and to. We have to find those intersection points. So we need to treat it like we're solving a system. We're trying to figure out where does that parabola intersect that line. So we need to set 2 minus x squared equal to 1, like we're solving that system. So subtract 2, divide by -1, x equals plus or minus 1. So that means we're integrating from -1 to 1. Bless you. Okay, now the fun part. I need to figure out what r is. So here's what goes through my head. I'm going to draw a rectangle to figure out what r is. And the rectangle I'm going to draw, I always draw it from the line I'm spinning around. So I'm going to draw it not from the x-axis like I did on the last problem, but I'm going to draw my rectangle from y equals 1 up to the function right here. And whatever the length of that rectangle is, that's r. Anybody know what the length of that rectangle is out of curiosity before I tell you? I'm gonna give you a hint. It's not just the function. It's not 1 or 2 minus x squared. 2 minus x squared.
Well, I guess, I mean, add 1 to it, so I guess 1 minus 2.
3 minus x squared? Huh? 1 minus x squared. What did you do to get that? Yeah, so let me explain. It is going to be 1 minus x squared. So, and I'm going to give you some hard and fast rules that you're not going to have to like memorize this stuff. My third year teaching this class, I finally learned like, oh, this works every single time. So, but I'll explain. So the length of that rectangle, that red rectangle right there, is whatever this distance is right here. When I draw from the x-axis up to that function, that black bar right there, the length of that is 2 minus x squared. Like that's the function length. But that's not what I'm after. Then I need to take away whatever this distance is from the x-axis to 1. So basically the length of that rectangle is the function value, that black bar, and then take away the distance to 1, which is 1. So big R in this problem, or I say big R because when we get into washers, we're gonna have a big R and a little r. Our R on this problem is going to be 2 minus x squared minus 1. So the hard and fast rules that I've learned is this. If you are revolving around an axis, whether it's the x-axis or y-axis, yeah.
Doesn't matter if you simplify that to a big R?
No, I would simplify it. I would do this, but it doesn't matter. So the hard and fast rules are this. If you're spinning around an axis, whether it's the y-axis or the x-axis, your R values are the functions themselves, always. If they say spin around the x-axis or spin around the y-axis, your radiuses, radii, doesn't sound right, but your radii are just the functions themselves, always and forever. If you're ever spinning around a line other than the axes, so if they say spin around y equals 1, spin around y equals 2, spin around x equals 3, something other than the axes, your R's are always the function minus the number. Always. Function minus whatever the number is that you're spinning around. Like on this one, if they said spin around y equals 4, the radius would be the function minus 4. So it's either the function or the function minus the number. And it actually doesn't matter if you do the function minus the number or the number minus the function. It doesn't matter which way you do it because you're squaring that value anyway. And you're always going to get to the same value. But now I'm just going to plug that in here. So it's going to be 1 minus x squared squared. Yeah.
Will we ever be tasked with like doing this with a function with a slope? Like instead of having it be y equals 1, have it be like y equals 4x.
Like the line you're spinning around?
Yes.
No, not in Calc 1.
Okay.
That I think will be a Calc 3 thing. From what I remember. Calc 3, from what I remember, very long time ago, half my life ago, which is scary, is all Calc 1, but then in the third dimension. So it's like everything we're doing here, but then you do it all in 3D. I remember Calc 3 being a lot easier than Calc 2, though. Remember that. Because of time, I'm just going to go ahead and say we take out Math 9 and we beep bop boopy doop doop and we get our answer. So 3.351. Some mistakes though I find students make with their calculator, I find this all the time and students get so mad, is I'll have students set it up correctly. Like they'll do this. And then in their calculator, I have so many students take their calculator, they'll do Math 9, they'll enter the integral, they'll be like, I'm going to do this. And then in their mind, they're like, and then I'm going to multiply by pi at the end. And I have so many kids, they'll do Math 9, they'll plug in the integral and the function, push enter and get the value and be like, boom, and then they write the value down and forget about the pi. So I would encourage when you guys are doing these in your calculator, I would push pi first, then Math 9. You're allowed to do that. Math 9 doesn't have to be the first thing you do. Push pi, then Math 9, and it'll multiply pi by that integral. So that way you don't forget. But I find so many people forget that. So just be careful. You didn't get that answer?
Did you have the time? I got 4.1.
Well, here, see if we enter it the same. So I would do pi, then math 9 from -1 to 1. And then I would do parentheses 1 minus x squared, parentheses squared. You didn't what? Ah. You'll never make that mistake again. For the rest of your life, all the calculus problems you do, the rest of your life, you will not forget that. Well, what the heck are you doing, Evan? Okay. 1 minus x squared squared. I don't think you want this parenthesis. The parenthesis you closed off after the squared is closing off the thing. So you have 1, 2. That last one closes that one. It's not gonna make you put it, but I went through high school and college with an 83 plus, so I'm very familiar with the intricacies and getting syntax. I've seen so many syntax errors, and I get so frustrated. Then I started teaching this class, and Miss Conti, she used to teach here, but she gave me the 84 plus. And I was like, this is so much nicer. There's not much difference between this and that though, in terms of like the notation. That's nice because that's color. Yeah. But I don't need the color. I think it's good for students, but yeah. I had someone leave one of those calculators in here a couple years ago. Like, no, I asked all my classes, I sent out Canvas messages, like I didn't want to just take it. Then school ended, and no one claimed it. So my wife took it from me. So that's her calculator now. Okay. I should have given her this one. That was nice. All right, so if now we are going to revolve around a vertical line. So now I always say like you're spinning it horizontally. It makes sense to me. So when you hear me say spinning it horizontally, that means around a vertical line. Like those two things mean the same thing in my brain. I don't know, but so like this one has us taking this region and spinning it around the y-axis. All of our thought process is the same, but now everything is in terms of y values. Everything, the functions have to be in terms of y's. The limits of integration have to be y values. Everything has to be y's. So it's the same formula. It's going to be pi. And our integral, you know, it's the same, but I'm going to say c to d just to emphasize those are y values. So from like bottom to top. And then our r is going to be in terms of y, dy. So you don't get to choose if you're in terms of x or y. The problem dictates. So we're spinning the square root of 16 minus x squared, so this little quarter circle, around the y-axis and creating like a igloo, dome. I don't know. I guess in reality it's a semisphere, like the northern equator. Okay. All right. So our volume is going to be pi. Now, this is not the best problem to emphasize the limits of integration, but we're integrating from the bottom to the top because we're in terms of y values. So our bottom is going to be 0 all the way up to 4. The reason it's not ideal is because you could screw up and use the x values and get the same limits on this one. Our function has to be in terms of y values. Right now, the equation given is in terms of x values. So we actually need to solve this equation for x. When everything's in terms of y's, we need to make sure that our equation says x equals, and then everything is in terms of y values. So square both sides. Feels so nice out there. Is it nice out for those of you that were outside before this? I just want to be outside. That's all I can think about right now. And I just hear the wind out there. Like, Okay. All right, so then I'm solving for x. So I would add x squared and subtract y squared. So I added x squared to the left, subtracted y squared, and then I'm going to square root. So that's the function that I'm dealing with. And then I need to ask myself, am I spinning around an axis or am I spinning around some other number? If you're spinning around the x or y axis, the r value is the function itself, always. If you're spinning around, x equals 2, then it's 2 minus the function, or the function minus 2. Doesn't matter which way you do it. So since we're spinning around the y-axis, this right here is our radius. So inside of here, we would put the square root of 16 minus y squared dy. And again, because of time, I would go beepity bop boop poof, math 9, 134.041. So those are discs. Okay. I'm going to show the rest of the 2-minute video here really quick, but I also want you to see, like on the next example, when we would do the washer method. I want you to notice on the next one, we're not going to do it, but I want you to see like when. Yeah. You just use X. Your calculator doesn't know if you have X's or Y's or whatever. You just always use X as your variable. So on this one here, we have this little leaf petal, rose petal that we're spinning, and we're spinning it around the x-axis. So what I want you to notice is there is space between the x-axis and the thing I'm spinning. When that happens, that is a washer problem. And that's what I'm going to show you in the video, okay? And then we'll do the problem. All right. So, AirPlay, switch, source, time me, code. Oh, good, because I'm not doing so hot. 9, 2, 7, 8. Nope. Oh, no. Stop share. It's going so slow. No. What is happening? No. Stop share. New share. Share screen. Google Chrome. Share. Maximize. Got it. What was it?
Well, I don't know. I had 17, but probably I had like
10.
I wasn't ready.
Get out of it. Okay. Here we go. All right.
Place X with 1.
And 2
everywhere we see it.
minutes.
We got a 1 here, and then we got a 1 here. 1 cubed is 1. So
Oh, there we
this is
go.
2
Perfect.
times 1/3. Oh, that's minus 2/3, and a 1 here gives us minus 1/5, and then minus, let's see, negative 1 in place of X, and so on. So it's pretty arithmetic from here, and then we just collect as we normally would. We find the volume to be 16/15 pi for this figure. In the previous 2 examples, the solids were truly solid. That is, they didn't have any holes in it. Suppose, though, we drill a hole in the solid. We can still make the calculations we're talking about. And here's what I mean. Imagine that we have this cylinder, and let's say that we drill a hole through it from one circular surface to the other circular surface, right through the middle. What kind of thing do we have when we slice it and look at a cross section? Well, we have a figure that looks like this. It looks like a washer. Now realize what this is. This is a cross section of that cylinder. So the cylinder would kind of come out this way and kind of go through the board, and we're just slicing it. And here's the cross section. Is what the cross section looks like. Now we're interested in the area of this cross section. And when we talked about the area of the cross section before, when it was truly a solid for that cylinder, it was just the area of a circle. You remember, it was the area area of the circles times the height is what we started with, and then it was an area of this circular surface times a certain width and so on as we develop the situation. But here, the area is the area of this washer. And we can really think of the calculation of the area as being the area of the big circle minus the area of the little circle. And let's see where that takes us. So the area of the surface of this washer is the area of the big circle minus the area of the little circle. Each of these is some pi r squared amount. The pi can be factored out, so we have big R squared minus little r squared. And the way that it manifests itself in the notation is like this. It's pi, then we have our interval, and we have this big radius associated with an x squared, and the little radius associated with an x squared. We want the difference between those two because of that situation up there. All right, here's a problem that uses this kind of technique.
So that's our formula. Instead of doing just pi r squared, do you guys remember back to geometry? You guys love geometry, by the way.
Oh, for sure, yes.
Proofs?
No.
I liked algebra or geometry because of my classes were like
Who'd you have?
Mr. Crow.
Oh, that sounds right.
Yeah.
And that was the first year he taught that
Yeah.
class. He didn't know what he was doing either. Mr. Craw. He's gone. He's an assistant principal at a Lapel Elementary this year. I still play cards with him, so we still talk all the time, but yeah. Okay, but in geometry, well, I imagine you would, because he didn't know what he was doing, so
But this situation occurs
He-
anytime.
Learned it though. I still got it. Some of it.
transitive property, CP, CTC, side angle side. Huh? The whole reason proofs are a thing, are you ever gonna prove triangles are congruent in your life? I mean, probably not. The likelihood is not high. But the whole reason proofs are a thing in geometry is just to teach the logical thinking, like how to create an argument. Like, this is true because, like, when you argue with someone, you don't just say, dang it, I'm right. You say, this is what I believe, and here are the reasons why. And that's what you're trying to develop your brain to do when you're doing proofs. Like, that's the whole point.
I think we did them in algebra, do better than geometry. I know it's easier.
Well, they start in geometry with the algebra proofs, like, you know, you add 5 to the right side, and then you say the addition property of equality. Then you divide, and you say the division property. So they start proofs with algebra.
Yeah.
At least, hopefully, you had a good geometry teacher that did it that way. Maybe not, I don't know, but anyway,
And the classes play on this training.
I don't need. Don't get me started. Don't get me started on grading policies that we do here. Okay. But what was it? You guys get me off track. In geometry, you have those problems. It's going to show off my beautiful ability. It's not terrible. Where if I say, hey guys, I want you to find the volume of this solid, right? There's like a cylinder taken out of the middle. And the way you do these, and you guys do them with area too, you find the volume of, like, as if this was an entire filled in thing, right? You find the volume of the entire cylinder. We'll call that like pi r squared h. And then you're like, but there's some volume missing, right? There's like a little cylinder inside of here that we need to take out of our calculation. So we got to take out that thing's volume. So we got to take out pi little r squared h. This is the formula for a washer problem. You're basically finding the volume as if it was an entire cylinder, but then taking out the volume of the thing that would be on the inside. This is your formula right here for a washer. Okay. So we're going to dive to the notes. When we are spinning around a horizontal line and there is space or gap between our revolution line and the 2D figure, we have to do washers. You have to do washers. So it's pi times the integral from a to b of big R squared minus little r squared dx. And it's in terms
Are we
of,
supposed to like see what you're writing?
no, because I didn't share the Elmo. Were you supposed to? Yes. Should you have been? No. But now you should. Can you see it?
Yep.
Sweet. Okay. So our job with the washer problem, we just have to find two different radii. But still, like I said, with the disk method, like your R's are either going to be the functions, always, or they're going to be the function minus the number you're spinning around, or the number minus the function. Doesn't matter which way you do it. And same is going to hold true here. So we have this region. And I don't like where they put that rectangle in there. That rectangle is like the worst rectangle placement ever. It doesn't help in any way, shape, or form. It's like, it has nothing to do with the problem. I hate it. I hate it. I don't know why they do it that way. We're spinning this around the x-axis, okay? It's a washer problem because there is space between the x-axis and the region I'm revolving. I have to do washers, which means I have to find a big R and I have to find a little r. And I'll explain the difference between those two here in just a second. So I know we're doing pi, the integral, and we're in terms of x's now, so we're going from left to right. So 0 to 1. I have to find big R and little r. So big R, I'm going to draw a rectangle from the axis of revolution, the x-axis, to the outer function, right? You're going to have two different functions. I'm going to draw my rectangle from the x-axis to the outer function. So here. And however tall that is, that's big R. However tall that is, that's big R. Well, since we're spinning around the x-axis, big R is just whatever that function is. Whatever that outermost function is, that's big R. The outermost function is the square root of x. That's our big R. For little r, I do the same thing, but now I just draw my rectangle to the inner function. Here. And however big that rectangle is, however tall that rectangle is, that's little r. But same idea. Since we're revolving around the x-axis, it's going to be the function. That function is x squared. A lot of times, so on the AP test, there was like a 6-year span from like 2008 or 2007 to like 2014, where one FRQ was solely devoted to area between curves, disks, washers, the thing we're going to learn in our last lesson, more volume. There was always one FRQ solely devoted to this topic. And then I started teaching this class, like right then, and I looked back at all the previous FRQs and it was always there. So I told my class, like, you're guaranteed to see one. Since then, there hasn't been an FRQ at all with this topic on it. They ask them in terms of multiple choice, but I just find it interesting how they decided to make that shift. My point is this: when you guys are doing FRQs, a lot of times they'll have these problems and it'll say like, write, but do not evaluate the definite integral that gives the volume. So make sure you read carefully. You can save yourself some time. A lot of times it'll just say, set it up and then move on with your life. So just be careful. And another reason I bring that up is because here's what you're allowed to do as far as a time saver. If you write like big R and little r here, you can actually do this in your work. And then you just move on. Like if you label what big R and little r are, you can do that and then just move on. So a little time saver. You guys can like name functions and then use those names within your work. It looks cleaner and they count it. So just something to think about. I'll fill them in here, but you can do it that way. So square root of x squared minus x squared squared. Beep, bop, boop, 0.942. You guys do know, maybe you don't know because I haven't said it. When you guys do FRQs, you don't have to write like Math 9, used calculator. Like you guys don't have to write those things. A lot of you do. It's not wrong, but I just see like a lot of people write Math 9. You don't have to. You just do this and then equals. They count it. Maybe. Yeah, I don't know, but I see it happen a lot. I never really talked about it, but there you go. If we're spinning around a vertical line, everything's the same. We're just now in terms of y values. time we got? Oh, yeah, got plenty of time. All right. Find the volume of the solid form by revolving the region bounded by y equals x squared plus 1, y equals 0, which is the x-axis, the y-axis, and x equals 1 about the y-axis. So on this one, we actually have to create our region. Just got to graph a little bit, just a little bit. So y equals x squared plus 1. That's your parabola. Shift it up 1 unit. It's ugly. So that's y equals x squared plus 1. We're bounded by the x-axis, the y-axis, and x equals 1. Just here. Just call it there. So we have to figure out what's the region. Well, we're bounded by the x-axis, y-axis, parabola, and x equals 1. So it's this thing here. That's our region, our 2D region. And we're going to spin that around the y-axis. So this gets really interesting. Is this a disk problem or a washer problem? Disk? Anyone want to say washer? Washer? If I said you're both wrong.
Well, I'm gonna watch the portion of
It's both. It's both. The reason it's both is this. So I want you to look at what happens here. So I just drew a little black horizontal line there. Everything below that black line, so this whole region here is flush with the y-axis. There's no space between the y-axis and that region. Meaning, as I'm spinning this thing here, this is a disk problem. There's no gap. But then above that black line, this part here, notice between the y-axis and that region, there's space there. There's gap. So I have to do a washer. So I actually on this problem have to set up 2 definite integrals and add them together. It's like you have 2 different things to do in this problem. Fun? That's sarcastic. Try again. So here we go. So the first thing we're going to do is the little part right here. Okay. So volume equals pi, the integral. Now we're integrating in terms of y's. So we're using y values, y limits of integration. So the lower limit is 0. The upper limit right here, because again, we're just doing this part right here. We're just doing this. The upper limit is whatever that y value is right here, which is 1. We shifted it up 1 unit. We're spinning around the y-axis, and it's a disk problem. Just for the lower part here. See, these are all the things that are going to have to go through your head. Is it a disk? Am I in terms of x's or y's? What's big R and little r? Am I revolving around an axis or a number? There's a lot of just things to think about before you just dive in. But yeah, there's a lot to think about, but there's hard and fast rules every single time. Like it works every single time if you have that stuff down. So big R, and in fact, just R is going to be however big this is right here. From the y-axis to that outer function, however long that rectangle is, that's R. That outer function is 1. It's the line x equals 1. Also think about it. No matter where I draw that rectangle, like the length of it is 1. So R is 1. So it's R squared. Oh, shoot. 1 squared. Mr. Jeter. The worst. This part right here that I just set up, that's going to find the volume of revolving this what looks to be a rectangle right here around the y-axis. But then we have to find the volume of the stuff above that black line. There are a ton of you on your tests not closing off your integrals with dx or dy. And I fill it in on every single one of your problems that you don't do it. Every single one. I have not taken off, but I fill it in. What they say is this: if there is just one integral in the problem and you guys forget to put it, you don't lose any points. But if there's an integral and then you're going to do like more, like we have to add another integral, if you don't close off the first one, you won't get full credit. So just try to get into a habit of always closing your integrals with dx and dy, just to be safe. All right, so plus, now I have to add the volume from that little top piece. So I'm spinning that top piece right here. I'm spinning this around the y-axis. It's a washer problem. Everything has to be in terms of y's, which sucks because the equation they give is in terms of x's. So we have to solve this for x. So I'm going to solve this equation for x, y equals x squared plus 1. So subtract 1 and square root. X equals square root of y minus 1. I have to integrate from 1 up to whatever this y value is right here. Well, that y value, well, think about what that y value is. That's whatever the parabola value is when x is 1. That's what's happening there. When x is 1, that parabola value is 2. 1 plus 1 is 2. It's a washer, so I need big R and little r. Big R is you draw a rectangle from the y-axis to the outer function. So here, big R is 1. So it's going to be 1 squared minus. And then little r is whatever the distance is from the y-axis to the inner function. But again, once you get good at these, you don't have to draw these rectangles. I'm doing it as a visual for now. But again, your r's are either the functions or the function minus the number. Since we're spinning around the y-axis, it's just the functions. So minus the square root of y minus 1 squared. That's your setup. They say the number one mistake on these problems is students will, instead of doing r squared minus r squared, they'll do big R minus little r and square that quantity. Those mean two different things, so be careful. Big R squared, I haven't ever had a student do it, but they say that's a big mistake. And then we go boop, 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 4.712.
Will these usually be calculated problems?
It will either be calculator or oftentimes it's set up but do not evaluate. Yeah. But these are all fair game to do it without a calculator. I'm just not. I don't like, yeah. You just don't want to? It wouldn't be that tough.
I know.
Yeah.
What do you get the big from like the second part?
The upper limit.
Yeah.
So I was integrating from this y value here, which was 1, all the way up to this y value here. This y value here is whatever the parabola value is when x is 1. Like, notice how 1 meets the parabola. So when x is 1, so if I plug 1 in for x here, 1 plus 1 is 2. All right, last one. I'm gonna have you guys try it yourself. Suckers. Here you go. This was from, I don't know what year, but this was a part off of an FRQ. I'm gonna put the answer up, but no peeking if you're not done. Yes, thank you. Another method called the shell method that those of you that are going into math in college will come across. It's not an AB topic or BC, so we don't do it, but you'll see it. Yeah, I was gonna talk about both. So I was gonna talk through this and I'll explain why that is. So, okay, when I go through this, as soon as I see I'm rotating, again, here's the catalog of thoughts that goes through my head before I start writing anything. First thing I think about is, am I in terms of X's or am I in terms of Y's? Am I spinning around a horizontal line or a vertical line? That's thought number one for me. Thought number two, I'm then like, okay, is it a disk or is it a washer problem? Do I need one radius or do I need two? Is my region flush the entire time with the axis revolution, or is there space between the revolution line and my region? That's thought number two. Thought number three is then, okay, am I spinning around an axis, like X or Y axis, or am I spinning around a number? Those are the three main things that go through my head. If you're spinning around, so first of all, I'm in terms of X's, so I'm spinning around Y equals 4. It's washer because there's space between that line and my region. And then I'm spinning around Y equals 4, which means my R values have to be either the function hi, what's up? I do. You want them? I was like, that was the big ta-da moment. And do you need the little connector?
Yeah.
Okay, it's in my bag.
Oh, no, this will work.
Sure. Pleasure doing business with you. See, what was I talking about now? Oh, yes. Okay. So since I'm spinning around Y equals 4, you can do it either way. You can either say the function minus the number or the number minus the function for two different reasons. Why? Reason number one, you're squaring that value anyway. Like when you do the function minus the number and then square it, imagine, so to put this into perspective, if I had to do 6 minus 3 squared or 3 minus 6 squared, it doesn't matter what order I subtract those two things. When I square it, I get the same value. Like this would be 9, this would be 9. So that's reason number 1. You're gonna get the same answer because you're squaring it. Reason number 2 is because these things are revolving. So like, yeah, right now 4 is above the function. So it'd be like 4 minus the function. But since this thing is spinning, I mean, this region is eventually going to be up here. I'm not going to redraw this accurately. You see, you get the point. That region, when you're spinning, will eventually be up here, and then the function will be above 4. So like they don't know at what point the rotation is in. So that's why it doesn't matter what order you subtract them either. But I wrote all this out to show you this, the difference in doing this is so much nicer. Like I would label these things big R and little r, and then I would write that as my answer instead of having to write out all this again. And then if you accidentally forget parentheses or you just forget a little thing, then you lose your credit. So you might as well just label it and do this. That's all I got, I think. You guys have questions? Yeah.
On the function, like the order, can you not just like say 2x squared minus 6x?
No, you should. Yeah, you can.
Okay.
Yep. They're equivalent.
Do you also write like f of x minus 4x?
Oh, that would even be easier. That would be nicer. Emma said instead of writing like, 2x squared. Yeah, I would do that. Now that I'm thinking about it. Just do this. Label it as f of x minus 4, and then that still works. And then the other one, you can do it as g of x minus 4. I like that even better. Okay, so Wednesday, I don't have anything for you guys to do. Is that okay? So Wednesday, you don't have anything to do. Friday, we are going to do some group work and practice this. There are some students I found over the years, there's some students that gravitate and pick up on this like really quickly, but there are a lot of others, me included, when I first learned this, that you need some more practice time. So you do have an assignment where you get to practice. You'll come Friday, we'll go over the homework, but then we're going to have a group work day just practicing like this stuff again. So you get another day of this. Then next Tuesday is our last lesson of the chapter of calculus. Then we have review the following Thursday and then test. That would have been awesome if that was the end of class and like the timing worked out that way. But anyway, that's the plan moving forward. I have no idea what we're going to do to review after the AP test. Normally, I would have everyone in here and we just play a bunch of review games, but I don't know what the people have to do at home. I haven't thought ahead yet. I'm not going to right now.
So we never, sorry, this is stupid. We were finding.
All right.
What are we gonna do after the test?
Nothing. Is that okay?
Also,
You guys at home, you are free to go. I don't think I did. Yep, you guys can go. And then I'm going to close this to record the Zoom.